Now, when we start using functions in the real world, we use functions to model relationships, all sorts of relationships. And so it's really useful to be able to get an idea of what the graph looks like, because that tells you what the relationship looks like. As you can see here, we managed to sketch the graph of each of these functions, but not all functions are like this. And so what I want to do is to go through and give us an idea of how we could sketch the graph of any particular function. And later on, when we get to calculus, we'll add a few more dot points in here. But for the moment, these are the things that are useful when we're sketching the graph of a function. I'll start here. So here we go. This whole box is important. So if you're sketching the graph of a function, it's useful to know the domain, the y-intercepts, the x-intercepts. Is it odd or even? If it's odd or even, then you only have to draw half the graph, and then you can just use symmetry to get the other half. Okay? So that's why we wanted to know about odd or evenness. We want to know the long-term behaviour of the function. I'll come back and talk about that. I've talked about it before, but I'll come back and talk about it again. And we want to know the behaviour of the function near asymptotes. And I've talked about that before, but I'll come back and talk about that again as well. We're going to have a go at sketching a function. We've actually done one like this before, but we didn't have this nice checklist of things to do. So it says, okay, first of all, the function that I'm going to use here is this one, 1 on x plus 1. So this isn't a polynomial function. It isn't an absolute value function, so it's not one that's in our regular library, if you like. It's actually what's called a rational function. It's the ratio of two expressions, a ratio of two polynomials. But the fact that it's a rational function is neither here nor there. Okay, so it says, first thing to do is to work out the domain of the function. That's a good spot to start. So let's go over here and think about the domain. So domain is a good spot to start. And what we're trying to work out are the values for which I can actually calculate this particular function. And we know that we can calculate x plus 1 any time, but we know that we're not allowed to divide by 0. So the thing in here is if this denominator is 0, we don't get a function value. Everywhere else will be right. So our domain is the set of all x values such that x plus 1 is not 0. And another way of writing that would be to say the set of all x values such that x is not equal to minus 1. So for every value except minus 1, there will be a point on the function. Now in this case, looking here, as x gets very, very close to minus 1, this thing here gets closer and closer to 0. As this is getting smaller and smaller, you divide a number by something very, very small, the whole thing becomes large. So this thing, as x is getting closer to minus 1, the function value is getting very large. And so in here, what this domain is telling us, so here, this function has a, and we use the word here, vertical asymptote. Has a vertical asymptote at x equal to minus 1. So a vertical asymptote, what we mean by that is it's a line that the function gets close to but never reaches. So if I were to put in here x equal to minus 1, which is this one, and I'm dotting it in because this isn't part of the function, but it's helping me think about the function. So that's the line x is equal to minus 1. That's my vertical asymptote. The function is going to get close to that, but it's never going to reach it. And well, what actually happens is, we're going to look at that down here. Look at the behaviour of the function near any asymptote. So that's the last thing we do. Oh, well, it doesn't have to be the last thing, but in this case I've got it there listed as the last thing. Okay, so that's the first part. The next thing is it says, well, the y-intercepts are always a good thing to do because they're relatively easy, usually. Not always, but usually. So y-intercepts. So the y-intercept is where the function cuts the x-axis. So it's the value of the function at x equal to 0. So it's f of 0 is the y-intercept. And so in here, my function is 1 on x plus 1. So it's 1 on 0 plus 1. And so that's 1. So this thing has a y-intercept of 1. So that means it passes through the point 0, 1. So I can colour that in there quite nicely. Can you see that? There's my y-intercept. Passes through the point 0, 1. That's good. It's also handy, if we can, to work out where it cuts the x-axis. We did that for the parabolas. Let's work out the x-intercepts. So what I want to know is I want to know for what values of x is the function 0. So I want to solve 1 on x plus 1 is equal to 0. Now to solve an equation, we try to make x the subject. So in here I would multiply both sides by the number x plus 1. When I do that, 0 times anything is 0. On the right hand side I get 1. So no matter what value of x I choose, I can never make that thing true. So this tells me that that equation has no solutions. If the equation has no solutions, the only interpretation of that is that the function never cuts the axis. Function never cuts the x-axis. So at no point does the function ever cross over there. That's interesting. Didn't help us, unfortunately. So that sort of didn't add too much extra information to our graph. The next thing to do is have a look, is this thing odd or even? Odd or even? And as I say, if it turns out to be odd or even, I really only need to then do half the graph, and then I can do the other half just by symmetry. So it cuts my workload in half. Now, I can see already that I've got x equal to minus 1 sitting here. That's not going to give me any symmetry. I'm not going to get much out of this, I don't think, but let's do it anyway. So function minus x is 1 over minus x plus 1. That's not function x, so it's not equal to function x. And minus function x would be minus 1 on x plus 1, which is different to that. So it's also not equal to minus function x. So this thing is neither odd nor even. So sad face, that didn't help me. It was worth a try though. It was worth looking at. So we've done that one, that one, that one, and that one. We now come to this one. The long-term behaviour of the function. So that's math speak for saying what happens to my function as x gets very, very large out this way, or very, very, I guess you could say small, but goes a long way along the negative axis. So, our long-term behaviour in here, long-term behaviour. I'll just write long-term because I'm too lazy to write behaviour. First thing is I want to know what does my function look like as x gets very, very large going off to the right, as x goes towards infinity. That's my terminology for what happens as x goes towards infinity. Now here's my function. As x gets really, really large positively, let's put in some values. Let's put in x equal to 100. 1 on 101, quite small. If I put in 1,000, 1 on 1,001, even smaller. So this thing is getting smaller and smaller and smaller as I go out here. It's getting closer and closer to 0, in fact. So I can say as x goes towards plus infinity, my function goes towards 0. And in fact, I can do better than that. I can say this thing is always positive if x is positive. So not only is it going towards 0, it's going towards 0 from above, is what that little symbol means. So there's a nice fancy sentence. It says, as x gets very large through the positive values, f gets very small, goes closer to 0 from above. And so I can actually fill that in over here. As x is getting large, this is getting closer and closer and closer to 0, but it's always above the axis. It's getting closer to the x-axis, but it's always above the x-axis. What happens if I go the other way? What if I go along the x-axis the other direction? So as x goes towards minus infinity, what happens to f in that case? Can we tell? And once again, if I put in a number like 100, minus 100, this would be 1 on minus 99. So that's fairly small. It's negative. If I put in 1,000, this would be 1 on minus 1,000, I should say. That would be 1 on minus 999. Smaller. And as x gets bigger or larger, has a larger magnitude, goes further out along the x-axis, that number's getting closer and closer to 0, but it's always negative. So it's going towards 0 from below. So we can say f goes towards 0, but from a negative perspective. And so it's, if I put it on my graph out here, it's going like that. Combine those two things together, along with the fact that we know this never, ever, ever cuts the axis, and we can say we actually have a horizontal asymptote here at y equal to 0. The x-axis is in fact a horizontal asymptote in here. So I'll just write that in. So, aside, this tells us that y equal to 0 is a horizontal asymptote. And that makes you sound really smart when you say that. Using big words. Okay. Probably won't get you very far though. Most people aren't impressed by such things. But anyway. All right. So, in this case we have some asymptotes. And so we want to try and work out the behaviour of the function near the asymptotes. We've got the horizontal one here, that came out in the wash. But we've got this vertical one. So what happens to the function as x gets closer and closer to minus 1? And in here, we need to check two cases. So let me go here. What happens with our asymptotes? So as x gets closer to minus 1, and I'll say here from the right-hand side, from values that are a bit bigger than minus 1. So I'm coming along my x-axis this direction. So, for example, if I put x equal to 0, I know the function value is 1. If I put x equal to minus a half plus 1 is plus a half. 1 divided by a half is 2. So it's up there. If I put in a third, this would be 2/3, 3/2 would go up to there. So what happens is this thing's getting closer and closer to minus 1, so it's getting smaller and smaller, so this is getting larger, but the values are always positive. So what the graph must do is it must go up there towards plus infinity. So as x goes towards 1 from the right, minus 1 from the right-hand side, f goes towards plus infinity, is what you have to think to yourself. What happens on the left-hand side? It could be the same or it could be something different. So let's go towards minus 1 from the left-hand side. So I'm coming in here this way. I'm choosing values of x. I'm getting closer towards minus 1. So, for example, if I put x equal to minus 2. Minus 2 plus 1 is minus 1. 1 over minus 1 is minus 1. So that would be there. Likewise, as I get closer, here, minus 1.5, minus 1.25, and so forth, that value will always be negative because this number is slightly bigger than minus 1. So that's always negative. It's getting larger and larger, but it will always be through negative values. So in fact, it's going off down here like this. So we would say f goes towards infinity. We know it goes towards infinity because it's getting closer to 0, but the values are always negative. And so now we can take a leap of faith and join all these bits up. And this one will come here like this. And that gives us a sketch of our graph. Now, as I say, there's a bit of a leap of faith. How do I know it doesn't bobble around in here? Well, calculus will tell us that there are no bobbles sitting in there. So for the minute, we're just happy with that. We're going to reckon that's as good as the graph that we can do. So it's in two parts. That is actually the graph of a hyperbola in there, but that's neither here nor there. The important thing is that we've gone through and we've got ourselves a collection of information that will tell us the main features of what the graph looks like. So if you work your way systematically through these things, you should always come up with something that's pretty close to the graph of the function. And as I say, when we do calculus, we're going to add some bits in the bit, some bits extra which says there might be some bobbles, it might bobble around a bit, and we'll find those via calculus. Okay, so we'll just leave that there. So that's your first approach to sketching. There's another approach that we can sometimes utilise. So that, as I said, that's one approach. Go through that. The other approach is to actually start with the graph of a function that you know and then modify it. I'll leave that under there. So, sometimes we can produce the graph of a function by thinking of it as a transformation of some parent function. So I'm going to do this by example, I think is the best way. So let me just highlight this and say this whole box here is really important. Okay. In your notes, I think all of that box is spread out across 3 or 4 pages. So I've just put it together in one spot for you. In there. Just sort of seemed to make sense to put it all together. But it is all there. It's all sitting in your notes. So it says here, as I said, I'm going to go through each of these, but it's probably easier if I do it by example rather than just reading out what it says. So it says here, sketch the graph of the function x squared plus 2. Now this is fairly easy, but the idea is what we're looking for. So in this case, we start with, let's say we know the graph. We know the graph of y is equal to x squared. We know the graph of, I might even say function x is equal to x squared. Let's start with that. That will be our parent function, if you like. Okay, so that's the one that we know. So, I might just come over here and sketch it. And I should have chosen something other than parabolas because I'm crap at drawing parabolas, but anyway. Here's minus 2, 4, 2, 4. So I might come around this way. Let me just dot this in for the moment. Can you see that? That's going to be my first function. So that's my parent function. We know the graph of function x is equal to x squared. Starting from that, we should be able to draw all of these very quickly. So goes the theory. Look up here at the first dot point. It says the graph of y is equal to function x plus a constant is the graph of y is equal to f of x shifted k units up the y-axis. So I'm going to make use of that one here, and we'll see that it makes sense. So I can say the graph of y, I should call it f, shouldn't I? F equal to x squared plus 2. That's the graph of y is equal to x squared. Now my constant here is plus 2, so it's moved up the y-axis by 2 units. That's what the first one tells me. And I think that should make sense, because if I pick a value for x, let me choose x equal to 0, say. On the graph here, y is just 0 squared, whereas in this one it's 0 squared plus 2. Likewise, if I choose x equal to 1, the y value is 1 squared, where here it's 1 squared plus 2. So for every value of x, all I have to do is add 2 to it. And so to draw the graph, all I have to do is just slide this up 2 units. So up 2 units and draw it. And this will come down like that. And there is the graph of y is equal to x squared plus 2. That's all I had to do. All I had to do was move the graph of x squared up the axis 2 units. Are we happy with that? So far? Okay, good. Sorry? Define happy. Seems plausible. might be a definition. Okay, the next one. Let's draw g of x. So I'm getting really fancy here. I've decided f for function's not imaginative enough, so now I'm calling it g, which is good. A, B, C, D, E, F, G. It's the next letter after f. Here we go. It says the graph of y is equal to minus function x is the graph of f of x reflected across the x-axis. So the graph of g is equal to minus x squared is the graph of y is equal to x squared reflected across the x-axis. So given that I know the graph of x squared, I can draw the graph of minus x squared. And again, I think it makes some sense, because again, choose a value for x. Just say I choose x is equal to 1, then on the graph of y is equal to x squared, that's 1 squared, whereas this one is 1 squared, and then you just take the negative of it. So instead of saying here's 1, go up, you go here's 1, go down. Likewise, minus 1, go up, but then I've got to take the negative of it, so I go down. And so this graph will look like that. So there's the graph of y is equal to minus x squared. It's just reflection in the x-axis. So given that I know my parent, I can very quickly sketch either of those two graphs there. So that's the first two. Let's do the next one. And the example is here, h of x is 3x squared. So the graph of h is equal to 3x squared. That is the graph of y is equal to x squared stretched vertically by a factor of 3. And I might do that one on here. I've got the graph of y is equal to x squared sitting here. If I pick a value for x, again let me choose x equal to 1. On x squared I calculate 1 squared and I move up to 1. So 1 lies on it. Whereas if I've got 3x squared, it says it'll be 3 times whatever had the value before. So I'm going to move up. Instead of being 1, it will be 1, 3. Likewise, in 0, 3 times 0 is 0, 3 times minus 1 is 3. And so I've just got this graph and I've just pulled it up by 3 units, if you like. So this graph goes like this. It's stretched by a factor of 3. Now that's a pretty wonky looking parabola, but that's the graph of y is equal to 3x squared. So it's not moved up 3, it's stretched by a factor of 3, is the idea.
If it was minus 3x squared, you would just times it by minus 3x.
I wouldn't, I'd do it as 2 steps. I'd do the 3x squared, then I'd do the reflection. Okay? Yeah. So then I would just take that and flip it over. But, I mean, that's equivalent of multiplying by minus 3, yeah. And the last one here is not as immediately obvious, but we'll do it anyway. So here, the graph of function x plus k is the graph of function x shifted k units to the left. So I'll write it down and then I'll, so part D here. The graph of m is equal to x plus 1 all squared is the graph of y is equal to x squared shifted to the left by 1 unit. So we need to have a little think of that. So let me come down here again, and here's my parent function, y is equal to x squared. Now the one that I'm interested in this case is m is equal to x plus 1 all squared. Now what this says is I take a value for x, then I have to add 1 to it and then square it. So if I put x equal to 0 here, I get 0 squared. To get the same thing here, I have to put x equal to minus 1, because I go minus 1 plus 1 is 0. Right? That's 1 unit to the left. Likewise, just say I had what happens here at minus 1. Well, I have to put x equal to minus 2 here, because minus 2 plus 1 is minus 1. So everything that's happening at x in this graph is happening at minus x, 1 unit to the left in this graph. So the fact that this one cuts the axis, or goes through 0, 0 here, on my next one it's going to do it there. The fact that I've got 1, 1 here, it's going to do it here. Everything moves across. And just check, I'll draw that in first. Minus 1, 4, minus 3, 4, so it'll come here. So there's my graph of m is equal to x plus 1 all squared. And just checking, what would be the y-intercept? The y-intercept would be the value of this when x is 0. When x is 0, it's 1 squared, which is nicely 1. In this. That's very nice. So in here, x plus 1 all squared is the graph of x squared shifted to the left by 1 unit. Had this been x minus 1 squared, I would have shifted to the left minus 1. So that's the same as shifting to the right. Okay, so if there's a minus sign there, shift to the right. If it's a plus sign, shift to the left. Okay.
Why is that different to the first one we did where, so
Yeah.
that equation out with x squared plus...
Look, go back to your first one here, this one here, x squared plus 2.
Yeah.
This one you did the x squared, then you added. This one you're adding and then squaring. Right? It's the order in which the operations are done. So when you're adding afterwards, it just shifts the graph up. When you're adding before you do the squaring, it shifts the graph to the left. Okay? Or the right if it's negative, as the case may be, yeah. And of course, if this one's negative, it goes down. So it depends on where your constant appears in your formula as to its effect. Okay? All right. So those ones were meant as examples of these 4 things here. And so we're supposed to now be clever enough to utilise these in all sorts of situations. So let's have a go at that. Here. So let's sketch, and we haven't got very many examples to work off, but we know about absolute value functions, so let's do these ones. So the idea is we're supposed to know about the graph of, we know the graph of f is equal to the absolute value of x. That's the one we know the graph of. It looks like this. So I'll just dot it in. This is my parent function. So that's y is equal to the absolute value of x. And I'm going to modify that function. And I think what I need is I need to have these visible. So part A says, let's sketch the graph of the absolute value of x minus 3. So that one is an example of this one here. It says, if I add k, it's shifted k units up the y-axis. In this case, my thing's negative, so it's going to go down the y-axis 3 units. So the graph of f is the graph of y is equal to the absolute value of x shifted, I'll say down the y-axis 3 units. Or you could say shifted up the x-axis minus 3 units, if you wanted to do that. So let's go down 3 units. Here it is. Do better than that, like that. And it goes up there like that. So this is the graph of y is equal to the absolute value of x minus 3. Ripper. Yeah, no worries. I'm not using it. So that's it. Know this graph, can immediately draw that graph. Now, we could have done it what we did before and turned this into a piecewise function and draw both bits, but this is just showing you another way to do things. Part B. I have g of x is equal to the absolute value of x minus 3. So have a look. That looks like it's the bottom one here. The graph of function x plus k is the graph of function x shifted k units to the left. So here I've got minus 3, so it's going to be k units to the right in here. So the graph of g is the graph of y is equal to the absolute value of x shifted to the right by 3 units. And so all I have to do is go over to here. And there will be the graph of the absolute value of x minus 3. And that seems pretty reasonable, doesn't it? If I put x equal to 3, it's 0, the function value is 0. Put x equal to 4, 4 minus 3 is 1, yes, it's going through 4, 1, and so forth. So it seems to match up. But the idea eventually is you can just look at that and say, okay, I know what the picture looks like. Part C looks a little bit more complicated. So I'm going to do part C in stages, in fact. So, in this case, we're trying to work out h is equal to minus 2 times the absolute value of x minus 3 minus 1. So the way I would do this is I would split it up and do it as a sequence of shifts, if you like. So I would start off and I'd say the graph of y is equal to the absolute value of x minus 3 is the graph of the absolute value of x shifted to the right by 3 units. We just did that. Shifted to the right by 3 units. So I started off with the absolute value. And now I'm going to go over here. So I started off with the absolute value of x, and then I shifted it over. Here's y is equal to the absolute value of x minus 3. I'm eventually trying to work my way up to this one. So far I've only done that little bit. So the next thing I want to do is I want to multiply by 2. I know that's going to stretch the graph vertically by 2 units. So I'll now say the graph of y is equal to 2 times x minus 3. Now I've multiplied 2 lots of x, absolute value of x minus 3. So it's going to shift the graph of y is equal to the absolute value of x minus 3 vertically. Is the graph, I'll say, stretched vertically by a factor of 2. So I've got this graph here, and I've got to pull it up. I've got to stretch it that way. So instead of going through there, it'll go through here. Instead of going through there, it'll go there. So it's going to look like this. I'm terrible at straight lines, but anyway. So this is going to be y is equal to 2 lots of the absolute value of x minus 3. I've taken that graph and stretched it up by a factor of 2. Having done that, I can now quite happily work with the minus. All I have to do now is reflect that over the x-axis. So now the graph of y is equal to minus 2 lots of the absolute value of x minus 3. That's the graph of y is equal to 2 lots of the absolute value of x minus 3 reflected in the x-axis. So that is that one. That's y is equal to minus 2 lots of the absolute value of x minus 3. So I've shifted it across, I've stretched it, I've reflected it. And the last thing I have to take into account is the minus 1. And of course the minus 1, that's just done last, so I now shift that down by 1 unit. So now the graph of y is equal to minus 2, the absolute value of x minus 3 minus 1, is the graph of y is equal to minus 2, absolute value of x minus 3, shifted down by 1 unit. And so here I can get this, go down 1 unit, and that's the graph I'm actually after. So this is the graph of h is equal to minus 2, the absolute value of x minus 3, all over 1. Now, that made it look relatively hard, but you can do these things fairly quickly once you get the swing of them. So across, stretch, reflect, down. Now in this case, of course, you could have just rewritten that as a piecewise function and drawn it, and you would get the same graph. So this is just another approach to sketching graphs. So we've got two approaches. We've got the one where you go through and get all the information, or you can try and shift parent functions.